By the way, also, you guys need to use your triple E email to to get into the Zoom meeting, no? Okay. So triple E 131 is about electronic devices and circuits, no? So when we ask ourselves what are electronic devices, um, what comes to mind, no? We have, for example, resistors and capacitors, no? This is from your previous classes. Resistors, capacitors, inductors, no? Those are our basic circuit components. Kaso, in real life naman, kapag sinabi nating electronic devices, hindi ba, actually, hindi na ano, ayan, ang weird na ng itsura ng phone ngayon. Let's do some retro drawing na lang. No? So this is a retro drawing of a phone, 'di ba? Na sa taas tapos may keypad dito sa baba na parang 3 by 3. Yan. O, 'di ba? Retro na phone. So this is what common like what the commonwealth, no, the normal people say, and that is not to say we're not normal. This is what normal people say is an electronic device, no? And we ask ourselves, how do we use our electronic devices na alam natin to build this electronic device? Meron dito. And then, to marry these two concepts, we need to introduce some special types of devices, no? And these are the devices that we're going to be talking about in this class, no? That type of device, not the RLC, no? Not the resistor, not the capacitor, not the inductor, but some other types of devices, no? Okay, prerequisites for this class is typically 1, 2, 3, and 3, 6, 72. Again, contact me if if hindi mo pa na take yung mga prerequisites na to, you're gonna have to get a waiver of prerequisite. Also, we have two delivery modes for our classes. Actually, this is distributed among the sections. So for my sections, yung combination of face-to-face and asynchronous lectures. Um, kapag kapag every now and then babaguhin ko yung mode, no, for a specific day. So please wait for please be on the lookout on Discord for an announcement, no? Um for announcements kung makukuha mo ay kung face to face tayo that day or not, no? For next week, ang plano ko is Wednesday is face to face and Friday is online. But the thing is, apparently there are bar exams, no? So there might be a notice, we don't know yet, no? There might be a notice na isasara natin yung campus and mag-o-online classes daw dapat tayo on the coming Wednesday. No? Wala pa yung memo na yon. But in case it does come, magiging online class yung Wednesday natin, tapos gagawin natin face-to-face yung Friday instead. No? So, hold on for that one. Tayo to, no? Yung WFTM sections. Right. So, for course resources, tanong ko lang sa inyo, have you guys been auto-enrolled to the Triple E at to the Triple E 51 Oble? Hindi pa. Okay. Sige. So, someday, may enroll kayo doon. Sa Piazza ba na-enroll na kayo? Hindi rin. Sige. So, well, this set of slides could be found in the Uvlen naman, and you guys should be enrolled in the Uvlen na kapag nagawa na ni Ma'am Tess yung CRS Uvlen integration. So we'll just wait for that, no? So by the way, assessments include Assessments for us include quizzes on Uble, no? So, quizzes on Uble. Tapos, throughout the course, you're gonna have 6 problem sets for each general topic. So, the first topic is handled by me. So, you're gonna have one problem set for the first, for the topic that is covered by the first 2 weeks. Right. So, await nyo na lang na ma-auto-enroll kayo dun sa Oble. And then, kapag some of you are already enrolled automatically, tapos meron pang hindi naka-enrolled, then saka ako magbibigay ng manual enrollment key. Okay, so for the course schedule, no, ito yung topics natin. For the first part, we're going to focus on mostly semiconductor physics, no? Tapos, this part is actually mostly a review, no? Because you guys did answer dun sa Discord na, well, you know what BJTs are. Not sure if you know what MOSFETs are, but they're basically also BJTs. Iba lang yung symbol, no? Diodes and op amps, of course, these are also artifacts of the past. Paano bang tawag? These are also things that you will review, no? Kasi na-encounter nyo na siya in a class called EEE 123 before, if I remember correctly. Then we're going to have our midterms, and then we're going to focus on more hardcore discussion about transistor amplifiers, capacitances, and amplifier frequency response, no? So that last part is probably going to be handled by Ma'am Tess, and I will be back to handle two-port network and small signal analysis. All right. So, course materials will include a course guide, no? Basically, the syllabus. It's already in Oble, kaso wala pa wala pa kayo dun sa Oble, so maybe I'll upload it to the Discord for now, no, para ma-peruse nyo yung course guide and see if you have any problems with it. We're going to have lecture slides also every week, sample problems for every week, and online graded quizzes. Okay, apparently we're also supposed to give links to lecture videos from previous sem. So wait for that. Kaso minsan kasi hindi nasakto yung um parang material from last year as opposed to this year, no? So sometimes we're going to give links to lecture videos, but probably most of the time we're just going to give some detailed slides or record lecture videos ourselves. All right. So for grading naman, so we have, of course, the online quizzes, no? Pretty sure all of you have experienced doing a quiz in Uble naman, and that's still the same thing that's going to happen here. We have 6 problem sets. Sige, let's go back to this one. Ang distribution ng courses natin, I think, should be may problem set to, problem set to, problem set to, at saka problem set to, which accounts for 5 problem sets actually. So, I think isang problem set to, tas isa to, and dalawa yung problem set about small signal and two-port networks, no? So, let's see how that will play out. But there's supposed to be around 6 problem sets, which make up 15% of your grade. For this semester, binabaan namin yung contribution ng exams dun sa final grades. But it still makes up about 70% of your grade, no, each. 35% for the midterms, 35% for the finals. So please do not miss the exam. Though we will give a comprehensive exam at the end kapag may na-miss kayong exam. Okay, so grading scale, hindi kami nagbibigay ng 4 for this course. But the thing is, kapag nagland kayo between 55 and 60, you will also take the compre just like people who missed 1 exam. Kapag napasa nyo yung compre, you're going to go up to a 3. Otherwise, 5 na yun. Right? So, standard UP grading scale naman siya otherwise kung wala yung compre. no? Or standard triple E grading scale. I think kasi for GE courses 96 yata dapat to. Okay, so any questions about that? All right. So, kung wala namang questions, then ano, okay. Here are the instructors, no? So the course coordinator is actually Ma'am Tess. And the other instructors for this course, one is Sir Chicho, and the other is me, no? So hello, it's me. I'm kind of a fresh graduate, I think. Kung fresh pa ang 2 years, 2.5. Anyway, that's me. Hello, that's me at the bottom. Okay, so um, let's review no the Triple E curriculum. Triple E 131 is actually a very important course. Not because of actually I'm not sure if rumors still fly, no? Kasi I did mention, right, that my favorite course is the courses that were merged to become this course, no, which is Triple E 41 and Triple E 51. So those were my two favorite courses. But at the same time, those two courses were rumored to be filter courses, no? Where a lot of students tend to get stuck, no? I'm not sure if the same still applies to Triple E 131. Hindi not, kasi mas baba na yung portion ni Triple E 41 dito kaysa kay Triple E 51, no? So this is more mostly amplifiers, no? Kesa sa physics, no? But anyway, if you guys are interested in solid state physics, no, these first 2 weeks are where you're gonna shine, no, because this is like the most interesting part, no, like if I don't know if you guys have heard about bottom up and top down approach, no, as in kung bottom up approach ka, you start with the very basic devices, tapos you build better things with them like computer, no, kapag bottom up. Kapag top-down approach, you start with something very big that you want to create, and then you start discussing the building blocks of such things, like transistors. In this course, we're going to do a very extreme bottom-up approach, because you've seen from the Discord, no, that I started talking about electrons, and it's kind of antimatter equivalent, the whole, no? We're going to be talking about that. Anyway, these things are necessary kasi if the triple E curriculum is a bottom-up approach, no, then you're gonna start here and then you're going to get to triple E 141, which involves wave shaping circuits, which is how you start creating, well, things that form signals, no, like oscillators and um bistable, monostable circuits, no. So that's why this is a requirement for that one. Of course, you also need to understand how transistors work in order to be able to start creating your communication RF circuits like transmitters, receivers from, well, transistors, which they are made of, no? This is why we start from here, no? Also, you're gonna need it for power electronics. To be honest, how triple E 141 exactly leads to power electronics, I don't quite remember, but you're going to encounter a lot more of Mr. Op Amp in triple E 141. This is new curriculum kasi. Okay. Okay, so okay, that's it for the um curriculum slides, no? I think medyo maikli naman yung lecture natin for today, no? At hindi rin ako like in with respect to the fact that it's the first week of classes, no, it's literally the second day of classes kasi I think yesterday yung last day, yung previous day of class, wala pa akong binigay na sample problems, or wala pang binigay na sample problems. Hindi ko pala na ano, no? Hindi ko pala na-mention kanina. Sige. Let's go up. There's this thing that I skipped over, no, which is called the handler grade. Now, handler grade meaning kami yung bahalang mag-isip, no, per section kung saan namin kukunin tong grade na to. Of course, hindi siya darts, no? It's not 5% darts. This could be attendance. This could be seat works, no? Now, when I took this course under Ma'am Tess, what Ma'am Tess did was sometimes okay. um this is funny though. Okay, so what she mostly did was to hold seat works. Tapos yung submission mo dun sa seat work mo, yun yung attendance mo, no? Essentially. And that's what also I'm planning to do for this course. Of course, for my sections, but the thing is, no, yung attendance, sometimes I'm not going to have a seat work. So, magbibigay na lang ako ng attendance, which I'm going to give you guys right now. No? Um, Copy, link. Right. And to everyone. Okay. So, sinend ko sa chat nitong Zoom meeting yung Google form for today's attendance. Right. So maybe let's take a 5-minute break while you guys accomplish that Google form and while I'll also help some of your classmates try to get into the Zoom meeting. Alright? Sige. So, sorry. Forgot to drink water during the break. Sorry. Anyway, sige. Um, so, ang galing, no? Meron na kagad tayong analytics from the Google form kung what you guys think of the class, no? Um, so it seems that everyone's perception of this class is it's going to be hard, no? To be honest, I don't think so, no? Um, Kasi perceptions change depending on the results of exams, no? So it I think it does depend on the results of the exam. Kasi to be honest, I did teach 143, no? Not sure if you guys have taken that. Have you guys taken 143? I did teach 143 last semester and nagbago yung perception nila. Sabi nila it was going to be parang ang perception ng easy nung una is easy. Tapos there was like a particularly hard problem in one of the exams. Tapos nag-survey ulit ako and everyone said it was um not much easier than the other classes. No? So it does depend on the perception of the class. I think depende lang kung makuha niyo yung intuition, no? And that's my job and that's the instructor's job, no, para makuha niyo yung intuition kung bakit natin ginagawa 'tong mga bagay na 'to so that hindi masyadong mechanical yung math, no? It's like parang yung nirvana state of mind, yung big brain state mo dito sa klase na 'to, like kapag naintindihan mo talaga is alam mo kung ano yung magiging sagot bago mo pagawin yung math. Like ginagawa mo lang yung math para makuha mo yung sakto, but you know in what ballpark it's going to be, no? So that's like the type of intuition that I want to that we would want you guys to have in accordance to these things, no? Now, my other thing that I want to point out about the attendance, no? Is merong WFY na nagsisit in or mali lang to? Okay, so whoever you are, you may have, done a typo. Also, please don't, send the responses twice. Nag-take naman ako ng emails down. So I think hindi naman kayo makakapag-send ng response twice. Saglit lang. I-resend ko lang yung Google form for the attendance just in case that people still, some people just joined, no? Anyway, ayan. So, okay, welcome to week 1, no? Week 1A pala. Um, and our lesson for today is Introduction to Semiconductor Physics, no? And this one is really cool. So, materials, no? Our electronics are made of things that conduct electricity, right? Um, Benjamin Franklin, no? His kahit mo magsulat dito. Yes, yes I can. Benjamin Franklin, no? Hindi pala siya yung light bulb, sorry. Lightning rod, no? So Benjamin Franklin's lightning rod is a metal, right? And it was like the first type of electronic device, essentially. Kasi si Benjamin Franklin yung nakapag-isip na, okay, this is electricity. It's like blue fire. That's what he said, no? So, ano ba ang metals? Now, actually, just while I was making these slides, I was wondering, okay, we call metals, well, metals, no? And we know that they conduct electricity. But what is a precise definition of a metal in terms of what we know from chemistry? No? The thing is, these parts, no, are called earth metals, alkali earth metals, and rare earth metals, no? And these are called transition metals, no? Yung mga nasa gitna. Now, the thing is, what what is in common about those materials na sinasabi nating metal sila at yung iba hindi? Well, when I searched for it, no, apparently our most precise definition of metals, which people still disagree on, by the way, is to define them as conductors at 0 Kelvin, no? That is at absolute zero temperature. At absolute zero temperature, if electrons can move around in that material due to an electric field, it is a metal, no? Which is interesting. And by the way, I said na they have disagreement kasi apparently in astrophysics, no? In astrophysics, metals are defined as anything that's not hydrogen or helium, no? So apparently all of these are metals. Oxygen is a metal, carbon is a metal, you are a metal in terms of astrophysics, no? So kapag nakita ka nila sa loob ng star, they're gonna say, oh, wow, that's a metal. Anyway, this is the definition of a metal. No? Metals are anything that is still a conductor if you put it down to absolute zero. Now, this course is about semiconductor device physics, and semiconductors are the type of material that we generally always use for our circuits, no? So you've probably seen this thing. Okay, it's red here, no? Kasi para siyang yung ano, yung spider ni ano, nung tao sa The Incredibles, yung kalaban doon. And ano, may serial number siya like 2N3904 or something, no? This thing is metal, of course, no? Bakal yung nasa labas niya. Tapos this thing is plastic. Nasaan yung semiconductor dyan? Well, actually, if you wait, confirm ko lang, no? And everyone knows what a 2N3904 is, right? Thumbs up or unmute, say yes. Okay, nakita nyo na ang 2N3904. Okay, sa loob niyan, there's like a very thin sheet of a semiconductor, no? So that is the thing that we're looking at. And, you know, alam naman natin na this thing is important, no? So, this thin sheet inside the plastic is just there to protect it, no? So we're gonna find out kung bakit siya kailangan i-protect later on. Actually, on Friday, I think that, Friday ko nilagay yung part na yun ng lecture, no? But there's a thin sheet of semiconductor in the middle of that, which allows the BJT to retain its to have its properties, no? So yun. Anyway, semiconductors exhibit both metallic and non-metallic properties. Metallic properties like conducting electrons. Non-metallic properties like not conducting electrons, no? Or, paramagnetism and the like, no? Which is, as an aside lang yun. But magnetic properties, these things exist differently in conductors and non-conductors, no? It's an interesting part, but it's a graduate thing in microlab. So join microlab if you're interested in more of this. But anyway, no, semiconductors can exhibit both metal and non-metal properties. So the thing is, if we nudge semiconductors to become more metal or less metal through certain methods, no? Like adding a little bit of metal para maging alloy siya, maging like kind of metallic siya. Or the other, no? By making it more non-metallic by adding this guy or this guy, no? Then we can vastly we can vastly change how semiconductor properties work, no? So, okay, sorry. In this course, no, we're going to be talking mostly about silicon, no? Now, okay, silicon. Silicon ang gagamitin natin with a little bit of help from its neighboring friends, no? Boron and phosphorus. So, facts about silicon. Silicon is element number 14. It is right under carbon. No, you can see that there. It is right under carbon, and it has 4 valence electrons. No, what do we mean when we say valence electrons? Mga nakauno ng chemistry dyan. And actually, you guys didn't take chemistry in college, no? High school pa to. Can anyone say what we mean when we say valence electrons? farthest electrons from the nucleus. Yes, in a sense, they are that, no? So that's correct. By the way, good afternoon, sir. Will these slides be available somewhere after the discussions? Yes. These slides will be in Oble. Oh, actually, they are already there. Kayo yung wala sa Oble. So, await them there. But also after this, I'm going to be uploading them in Discord. Anyway, including the recording, no? Okay, so yes, valence electrons are electrons found in the outermost shell of an atom. And why are they special? Let's say that I have a carbon atom, no? We tend to bond carbon atoms to 4 other carbon atoms. Kasi yung valence electrons natin ang ginagamit natin to bond with other things, no? So, what's special about silicon is just like carbon, it can take a lot of crystalline configurations, the simplest of which we could represent as a two-dimensional sheet of every 4 silicon atoms na magkakatabi, no? And we're going to be using this lattice representation, no? Or lattice model of silicon a little bit, no? In this first lecture, no? So you can see here, we have silicon atoms here, 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 and here. Tapos, ang bawat stick dito is 1 electron, no? 1 electron that is shared between the 2 silicon, no? Kasi nakabond sila, no? So each silicon shares one of its valence electrons to another silicon. So vice versa 'yon nangyayari, no? So dalawa yung nasa gitna ng each a pair of silicon. Kasi nagshi-share sila ng electron doon, no? So this is our lattice model, and this is quite stable because it has sticks, no? The binding energy of the electron holds the lattice together, no? And having 4 valence electrons is important. We're gonna see why it's important later. Now, if you've never seen silicon, you have, no? Everyone's just lying to you kapag sinabi nilang hindi silicon. But if you've never seen silicon, look at concrete. No, concrete is made of rock and cement, both of which are partially made with rocks. No, so then those are also made of silicon. Kasi silicon is a part of silicates, no? And silicates are the predominant rock material, no? Silicon dioxide, no? Silicon dioxide, SiO2, is the material of silica, no? Which is a specific type of very pure sand, no? And it's used in industrial cutting mostly, if I remember correctly. Like if you've ever seen like may parang jet of water na ginagamit nila para mag-cut ng rock, no? That water is mixed with silica, no? Which is also, people also call it quartz sand. So it has industrial applications, yung very pure silica sand, but most other rocks are called silicates because they're made of silicon plus some other elements. Sometimes also silica, kaso marami pang ibang impurities doon. So that's why we have gemstones and such, no? Anyway. Okay. So, let's talk about conduction, no? Well, now that I've introduced silicon, no? In non-metals, electrons are either bound to the atom or shared in valence bonds, no? For example, in carbon, no? So carbon, 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 carbon. Sorry, wala akong ibang matandaang organic chemical bukod sa, actually hindi naman to stable na organic chemical. Anyway, for insulators, no? The electrons are always bound to valence bonds, no? They don't really freely leave the atoms that they're bound to, no? On the other hand, metal doesn't have a lot of metal has way too many electrons. No? It has way too many electrons that not all of them stay in valence bonds. Let's just say pure mercury, which is liquid at room temperature, no? But for illustration's sake, no? This is gonna have a lot of electrons and they're not going to be stuck at the highest orbital energy level. Kapag nasa highest orbital energy level na sila sa isang metal, the electrons are going to escape from their home atom and they're going to start sloshing around like water, no? So if you apply an electric field, these electrons are going to start swimming around in the opposite direction of the electric field, no? And because of that abundance, metals can conduct electricity very well. Now, lastly, we have semiconductors, no? Semiconductors only have very few conduction electrons, no? Much, much less than metals. And this is because of heat, no? So you can think of semiconductors as insulators. Kaso, because of heat, no, some of the electrons that are supposed to be stuck in the atoms can escape, no? So we have an electron, no? Tapos meron kang nucleus. And it's bound, no, by some energy. It's called the binding energy, no? Which is something on the order of like 2 electron volts for silicon, I think. But if you manage to give enough heat, no, to to yoink the electron out of that binding, no, then the electron is free to move around, no, which is why we have electrons moving around in the semiconductor, no, because of heat randomly giving electrons the ability to escape from the bonds of the atom. Now, keyword, heat, no? So, then, if I ask you if silicon is a metal, is it a metal? I mean, of course, I already wrote it in the slide, no? Dapat pala hindi ko nilagay dun sa slide. So, the answer is no, no? It's not a metal. Kasi ang keyword natin dun sa discussion is heat, no? Electrons need heat to be able to escape from the binding energy that keeps it in its atom, no? And only then saka pwedeng mag-conduct ng electricity yung free electron mo or your carrier electron as it will be called. So since it needs heat and at 0 Kelvin, absolute zero temperature, it is the complete lack of heat, no? Meaning silicon would not be able to conduct electricity because it has no carrier electrons in absolute zero, no? That's what makes it not a metal. But in a sense, also, that's what makes it semiconductor because heat can make it able to conduct electricity. All right. So, ito nga, no? As illustrated here, heat, no? Heat, this thing, no? Can be applied to a semiconductor in order to give energy to electrons to be able to escape their bond from the nucleus, no? So kapag naka-escape na si electron, of course yung silicon atom kasi because it lost a net negative charge, it becomes positively charged, right? Tapos si electron is free to move around, no? Okay. So, heat is applied, nag-escape si electron. Tapos, naiwan yung silicon atom. Silicon, no? Silicon is 14, right? Is atomic number, no? Atomic number 14, no? Ano ba ibig sabihin ng atomic number? Can someone tell me what the atomic number means? What does it indicate? Exactly, it's the number of protons, no? Kasi the number of electrons and the number of neutrons can change in a nucleus, no? If the number of neutrons change, we call that an isotope. If the number of electrons change, we call that an a cation or an anion, basta an ion, no? Anyway, an atomic number of 14 means we have 14 protons, no? And charge neutral ang silicon, no? It's not particularly charged, right? It's not an ion. So it also has 14 electrons. Kaso, because of heat, nakatakas yung isang electron, no? So we're left with 13 electrons and 14 protons, leading to a net positive charge, no? So the hole, no, as we call it, the space that the electron should have been occupying is now an empty space, no? A positively charged empty space, approximately, no? That's what we call it. We call it a hole, no? So an electron should be bound to a hole. But if heat is enough, it can knock the electron out of that hole and leave behind the hole. The hole is positively charged. And just like the electron, no? Holes can move around. Bakit? Kasi neighboring electrons can choose to jump into that hole. Eh kaso, sino yung papalit dun sa electron na yun? If this electron jumps into the hole, no? Then may bagong hole, right? So the hole moves around just like the electron does, no? So now we have, in semiconductors, we have negatively charged charge carriers and positively charged charge carriers, no? And okay, so physical constants, no? So fundamental physical constant, unit of charge is Coulomb, named from the guy who first demonstrated electric charge, I think, with balloons. Actually, I'm not sure if it's balloons. Maybe he demonstrated it with hair, but I do remember it's a demonstration that involved rubbing things together. Just like Google it if you, I know, if you're interested. But it's Mr. Coulomb. Okay, so electrons are negative Q coulombs of charge, and holes are positive Q coulombs of charge. No, this is 1.902 × 10⁻19 coulombs of charge. No, because electrons are very very small naman. Okay. So, in intrinsic material, no, we're going to be talking about what intrinsic material is, but basically it's vanilla silicon, no? So it's just unadulterated silicon, wala ka pang binabago sa kanya. In intrinsic material, the number of carrier electrons and holes, no? We represent those with the letter N and the letter P respectively, no? We can calculate them with this equation, no? So, generally, N and P, no, the number of free electrons and the number of free holes, no, we call them carrier electrons and holes, no. These are the ones that have conduct things or conduct electricity. Those are equal to Ni, no. Ni is the intrinsic carrier concentration. So Ni is the intrinsic carrier concentration, and N and P are equal to it at in a regular piece of silicon, no? So at 300K, depending on your semiconductor, the number of intrinsic carriers, no? The intrinsic carrier concentration per cubic centimeter, no? By the way, in this course, lahat ng concentration natin, we're going to be talking about it in per cubic centimeter. In room temperature, no? By the way, 300K is room temperature. Bakit? Ano ba to sa Celsius? Can someone tell me what 300K is in Celsius? $26, yes, no? So that is really close to 25, no? So essentially same naman, no? 25 is generally accepted as the room temperature. So 300K is generally accepted as the room temperature in Kelvin, no? So at room temperature, silicon, this is not the reason why we like silicon, but it's one of the reasons why I like silicon very much. Very nice number, 10 to the 10, no? So actually it's, sige, I'll ruin the dreams for a bit, no? It's actually 1.08 times 10 to the 10 apparently. But we round that off, no? It's 10 to the 10 free electrons and free holes at room temperature, no? In silicon, which is an astounding number. But it's much, much less than a metal. Bakit? 10 to the 10 is much less than Avogadro's number, no? This is much less electrons than there are in a mole of silicon, no? Than there are atoms in a single mole of silicon, no? So that's like one of the um like that's one of the special properties of semiconductors, no? We do have a lot of carrier electrons and holes, no, which is enough to conduct a lot of electricity, but it's much less than a metal because it's much less than the Avogadro's number. We we also have cameos, no, from the other semiconductor materials here, no. This is gallium arsenide. Now, okay, gallium arsenide. Gallium arsenide is interesting kasi kapag naglagay ka ng P, no, phosphorus, this becomes your first LEDs, no? Around the 1970s, they were fabricating light-emitting diodes, no? And they first made a light-emitting diode out of a gallium arsenide semiconductor, no? So that's pretty cool. I think next week pa natin, sa Friday pa natin mapag-uusapan kung paano gumagana tong mga tong mga LED. And I did promise na silicon tayo mag-focus. Trivia lang siya, no? So, gallium arsenide, this thing is typically used for for LEDs. Germanium, this is typically used for high-speed devices kasi kasi it's much more conductive, no? You can see that there. It's an order of 1,000 more electrons than more carriers than regular silicon. Anyway, those are the intrinsic carrier concentrations. Now, this relationship is important, no? So, let's erase all of these. This relationship is important. Bakit? Kasi if you know the number of holes, for example, in a material, no? Then this is now Ni squared over P, no? And vice versa. You can find the number of electrons that you have with respect to depending on the number of holes and vice versa, no? So paano ba nagbabago yung N at saka P, no? Bakit sila magbabago ng relative number, no? Bakit kailangan natin tong relationship na to? It's called doping, no? And it's not the bad kind of doping, it's a doping that we do intentionally, no? Of course, they also anyway. So, intrinsic material, no? Yung sinabi natin kanina, in intrinsic silicon, no? That's why it's called intrinsic carrier concentration. Intrinsic materials or intrinsic semiconductors are semiconductors that are not doped. They are like pure silicon, no? Walang ibang nakalagay sa kanya. Doping is the addition of controlled impurities, no, to the silicon crystal. Kaya ang sinabi ko kanina, 'di ba, na we're going to be discussing silicon with a bit of help from its neighboring friends, boron and phosphorus, no? Now, boron is 1 below this guy and phosphorus is 1 above silicon, no? The important part of that is the fact that boron would have 3 valence electrons, phosphorus would have 5 valence electrons, no? And this is interesting kasi if you sprinkle phosphorus atoms and boron atoms into a silicon lattice, capture sila nung lattice. They're going to think it's one of them, no? So it's going to be bonded to the other silicon. Kaso, phosphorus, no? Up here, phosphorus has 5 valence electrons, no? That's 1, 2, 3, 4, 5. No? Since phosphorus has 5 valence electrons, nagkaroon ng isang free electron right here. No? So then it's going to start moving around. No? It immediately becomes a carrier electron. No? Actually, not so immediately. There's like a little bit of time needed. But it very easily becomes a carrier electron, which essentially means na bawat phosphorus atom na ilagay mo, it becomes a carrier already. No? So, phosphorus, since it has 5 valence electrons, each phosphorus atom adds 1 electron, 1 carrier electron to the silicon. Next is boron, no? Boron has 3 valence electrons. So kapag dinagdag mo siya sa lattice, no, they adopt that's one of them, then its 3 valence electrons will be caught up in bonds. Kaso, ngayon, one of the silicon around it will not be bonded to that boron, no? Kasi kulang ng valence electron si boron. And what is the lack of an electron in a silicon crystal? That is a hole, no? So, pwede mo malaglag dito yung electron na to, pwedeng ganon, ganon, no? So, as before, we can have our lattice gains a hole that can move around, no? So, boron, no? Boron adds an extra hole when we sprinkle it into the semiconductor, no? Now, when we dope a semiconductor, we now call that an extrinsic material, no? So, it's not very difficult. It's intrinsic kapag hindi dope, extrinsic kapag not dope because it's not intrinsic, no? Okay. So, equations, no? We use these equations to find the number of carrier electrons and the number of carrier carrier holes, no? Once we know the doping concentration, no? Again, doping concentration per centimeter cube, ito, no? So, depending on the concentration of donors, no, and acceptors that we put into the material, we can change the number of electrons and holes. Kaso, or carrier electrons and holes, no? Kaso, the difference is hindi siya exactly nag-add, no? Kasi intuitively, 'di ba, ang sinabi natin kanina, each thing adds one uh, electron, right? But this is not necessarily the case, no? It still also depends on, say, the temperature, and it is also heavily affected, like it is very heavily affected by the presence of the other type of dopant, no? So kapag naglagay ako ng boron dito, no? Kapag naglagay ako ng boron dito, this electron can easily fall into that boron hole, no? And it could be stable like that. Kaya na-affect siya. Kaya kasama yung Nd minus Na dito sa equation na to and Na minus Nd dito sa equation na to, no? So merong interplay na ganun. But, okay, this equation is kind of ugly. I don't like it. So, anong pwede natin gawin? Assumptions, no? If the number of dopants, no? Like the concentration of donor atoms na nilagay natin is much, much greater than the intrinsic carrier concentration, and it is also much, much greater than the acceptor concentration, then the number of electrons is actually approximately equal to, basically equal to the number of donors, no? And ang intuition doon is I put it down here, no? Say for example that you put in 1,000 donor atoms per centimeter cube. Tapos, ang original intrinsic carrier concentration natin is meron lang isang electron per centimeter cube, no? Tapos, nag-dope din tayo ng isang acceptor per centimeter cube, no? By the way, donor here would be phosphorus, boron, acceptor would be boron. Bakit? Boron has less valence electrons, phosphorus has more valence electrons. So, kung 1 lang to, tapos 1,000 to, tapos 1 lang din to, kapag pinasok mo yan dun sa equation, you get 999.000, no? By the way, we're starting to get into the meat of it, that's starting to, throw math at you. Please feel free to unmute and chat kapag may question kayo dito, no? Anyway, kapag pinlog in mo yan dun sa equation na yun, magiging 999 to, no? Which is about essentially 1,000 lang din, no? In the same way, no, if you have one donor atom, 1,000 acceptor atoms, and the original intrinsic carrier concentration is 1, then you get 999, which is basically the same number of the acceptor atoms, no? Okay. So, frequently asked question, Sir, ano yung much greater than? Paano ko malalaman kung ano ang much greater than? Rule of thumb, if it's about 1,000 times yung difference, that is much greater than, no? Okay, at room temperature, the intrinsic carrier concentration of silicon is 10 to the 10. So then, if your dopant concentration is 10 to the 13 up, no? Then this is your new number of electrons and or holes, no? Assuming na walang ibang dopants, no? Kasi for example, no, kung 0 naman yung like actually this one is 10 to the 0 which is quite nice. Kaso kung 0 kung 0 yung number of Na mo, of course, magdo-dominate na din talaga to, no? So, in essence, no, essentially kung 10 to the 9 yung Na mo, this is your Ni, tapos this is your Nd, then Nd will dominate. Kasi it's more than 1,000 times either of these, no? It's a difference of 10 to the 3, yung much greater than. Anyway, yun lang yun. Okay, more definitions over here. Kapag nag-dope ka ng donors, N-type siya. Bakit? Kasi it's mostly charge negative, no? Actually, that's not exactly true, no? Negative kasi yung charge carriers niya na manggagaling sa kanya. Kasi electrons yung charge carriers niya. Kaso, ang tanong ko sa inyo, is this negatively charged? Kapag nag-sprinkle ako ng phosphorus dun sa semiconductor, do you guys think it's going to be a net negative charge? Yung block na yon. Kapag naglagay ako ng positive na, like didikit ba siya sa isang positive na electric, like na positive na voltage? Do you guys think? No. Why? The correct answer is no. Yes. No? So everything starts neutral. Everything is charge neutral. So pag pinagsama mo sila, dapat charge neutral. Ang nangyari lang is, di ba, nag-escape tong electron na to. It starts flying around. Then it leaves a net positive charge. Even though this electron starts carrying around a net negative charge with it, there's still a net positive charge where it left. No? So nagkakaroon lang ng charge difference within the silicon. Kaso, parehas pa din, no? Neutral pa din yung buong silicon block because everything that we use to create the block is still neutral, no? Now, we just call it N-type kasi electrons yung majority carrier niya as what we will call it, no? Electrons are the majority carrier for an N-type semiconductor kasi donors yung ginamit natin to dope it. Kapag acceptors naman, then maraming holes which are positively charged charge carriers, no? So yung majority carrier natin ay positively charged, kaya P-type yung semiconductor natin kapag acceptor dope siya, no? What about if both? Pwede kang maging pekeng intrinsic, by the way. Kasi if ND equals NA na hindi zero parehas, then it's essentially intrinsic kaso dope siya, no? So pwedeng nangyari yon, it's neither N-type or P-type, no, but it's dope. Anyway. Sige. So, on to a more interesting part, no? By the way, I may be like spending too long on some of these, but you know, we can always just move some of this lecture to next Friday naman kasi marami tayo. Medyo maikli yung lecture on Friday. Mas marami tayong mas to be honest, cool sa akin tong first lecture kaya I'm going to spend quite a while on this. Anyway, energy band diagrams. So in solid state physics, they use energy band diagrams to describe where the carriers are in materials, no? So, kapag sinabi kong electron configuration, do you guys remember what that is? Can you guys chat an example of electron configuration? Electron configuration ng silicon, for example. SPDF, those are orbitals. So, but close enough. Sige, let's start with that. No? Ito, no? This is the electron configuration of silicon. No? So, you have energy levels and you have orbitals in those energy levels. No? You have the s orbital, the p orbital. Tapos, actually walang 1p, sorry. Tapos yung mga orbitals is sila yung parang shape nung orbit nung electrons, right? That's what it is from chemistry, no? Now, as you go up in energy. Now, a secret that they probably told you, no, they should have told you in chemistry, I'm not sure. Kasi hindi naman kayo sa UP na chemistry, but the thing is, no, ang 2s at 2p, 3s at saka 3p, no, they are slightly different energy levels pa din, no? They're much closer than each other. Like for example, 'di ba? In the um Dirac, no. Uh Basta some guy who was wrong, no? He's still a very smart guy, but he was wrong about this. Niels Bohr, no? By the way, kung pinanood niyo yung yung Oppenheimer, Niels Bohr appeared there, no? He was the guy responsible for like yung gantong model ng atom, right? Yeah, so that was his mistake. Anyway, so eto 'di ba? Ito yung model Niels Bohr. Na meron kang mga electrons dito, mga to, spin up, spin down, no? Tapos parang if an electron gains energy, it can be promoted to the next energy level, right? So what he didn't tell you is within these energy levels, makakadikit pa may mga mas maliliit na energy levels and depende dun sa orbital mo, may difference 'yan, no? So for isolated silicon atoms, if we zoom in to this third energy level dun sa Bohr model, no? Then you get this picture, no? Yung 3p2 orbital mo is actually a little bit higher than the s2 na than the 3s2 na orbital, no? And these are where your electrons should be resting, right? Etong 2 meron siyang spin up at saka spin down na electron, right? But we don't care about spin for now unless we're doing magnetic devices, no, which is cool. But anyway, spin is related to magnetism. We're not talking about magnetism, so hindi natin kailangan pag-usapan yun. All we need to know is that there are 2 electrons in each of these, right? Now, the smart people in quantum physics, no, they did the math, no? Okay, sabi nila, kapag meron tayong system na dalawa yung silicon, no? Eh di ano na yung bagong orbitals natin? What are the allowable states, no? Ang iniisip nila. And this is an interesting read, by the way. So actually, I say read. This is an interesting Google, but there are these things called molecular orbitals, no? Anyway, kapag nag-bond na yung mga bagay na yan, dadami yung possible orbitals, no? That's essentially the thing. And they found na as you increase the number of silicon atoms, no? Padami ng padami sila and they get closer and closer together, yung number of yung discrete states na to, they get like there's more and more of them until you eventually end up with bands, no? They're essentially almost uncountably close to each other and uncountably numerous, no? So, in a crystal, no? In a silicon crystal, there's a specific distance between silicon atoms, no? In crystals, no? So, in crystals, may atoms, di ba? And they're like equally spaced to each other. Itong spacing na to, hindi siya na-violate for solids, no? For solids, hindi na-violate tong spacing rules na to. Actually for crystals, no? Solids can be like glass na amorphous siya, in which case na hindi followed yung rules. Kaso for crystals, there is a very regular distance between each atom, no? And it's called the lattice constant. Now, for silicon, this is around 0.543 nanometers, no? But anyway, if you do the math, apparently, the number of states, you can, well, of course, you can count the number of states. Kaso makukuha mo tong energy band diagram na to, no? The 3p2 and 3s2 orbital will merge together and then separate as well, no? So some of the 3p and some of the 3s turn into this, some of the 3s and 3p turn into this, but there's an uncountably infinite, not infinite, no, it's finite, but it's uncountably close together number of states, no, na may separate, no? So there's a gap between them, no? Right. So, paano nila na-count yung states na yun? Paano nila nalaman? Well, they made this equation, no? It's called the density of states, no? Bands are just densely packed lots of densely packed energy levels, no? So yung 3p2 at saka 3s2 mo, it became a lot of energy levels. Kasi nga, you have n atoms in the crystal, which means you have this much, no? Anyway, density of states. Now, density of states is a measurement of how many states there are per cubic centimeter in the crystal, no? In both the conduction band and the valence band. No, we're going to talk about kung bakit siya conduction band and valence band later on. Anyway, kaso, you just solve this equation. And all I want you to see here, no, for now, you can go back to the slide to look at the equation itself. Naman, no, this is full of physical constants. Is, ang shape nila is square root. No? So, the number of states increases as you go further away from the gap. No? Kaso may gap siya sa middle. No? If you solve these two equations, no, the number of states sa conduction band and the number of states sa valence band, they go up, no, as you go farther, and there's essentially no states that are exactly in the border, no? So yun yung gusto ko makita nyo, na square root yung shape ng solution nito, no? Other things to note, no? This is Planck's constant. Well, I'm not going to go into depth about how they got Planck constant. Pi, how did they get pi? Pininturahan yung wheel, tapos inikot, tapos nakita nila, uy, 3.14. De joke lang. The precise number of pi was probably obtained by Euler or something. Tapos ito is the density of states mass ang tawag dito. Kasi yung carriers natin, they have effective masses, no? And these are measured with respect to the rest mass of an electron, no? So, in terms of yung semiconductor physics na pinag-uusapan natin, actually, electrons, no, carrier electrons are actually a little bit heavier than carrier holes, no? So, yun lang naman yung sinasabi nito. Basta, if you plug in all of those, you find na yung density of states is actually square root, no? Anyway, sige. So, why is it called a conduction band and a valence band? Valence band to kasi dito sa model natin kanina, 'di ba? Na may mga sticks. Kapag nasa stick pa yung electron, no? Kapag hindi pa siya nakaka-escape, hindi pa siya carrier, it's in the valence band. No? You can see there's a lot of E in the valence band. Kapag naglagay na ng heat, no? Pwede mag-escape dun sa valence band yung electron. Kaso, there are no occupiable states here, no? The rules of quantum physics say that these things have to occupy specified energy states. It is impossible for them to occupy states that are not here, no? Hindi continuous, discrete yung number of states na pwedeng i-occupy ng mga electron, no? By by some guy's principle. Anyway, actually Fermi-Dirac statistics to it. Anyway, hindi siya pwedeng manatili dito sa gitna, no? It's actually called the forbidden gap sometimes because of that, but we call it the band gap. So the electron jumps from here to here if it's a carrier, no? So electrons in the conduction band are carriers, no? Tapos, yung electron na nag-jump up from the valence band to the conduction band, it leaves behind a hole, which we know is also a carrier, no? So carriers in the valence band are holes, and carriers in the conduction band are electrons, no? And the notable thing here is at 0 Kelvin, right? You won't find any electrons up here. You will find them all here, no? The conduction band is completely empty. As we saw here in this slide, right? We have 4n empty states up here and 2n plus 2n filled states, which is basically 4n, no? 4n filled states down there, no? At 0 Kelvin. So, the conduction band is completely empty. Valence band is completely full kapag walang heat. Kapag na-introduce ka ng heat, of course, mag-pop out na yung mga electrons. They start going to the conduction band where they are free to move around and conduct electricity. In the same sense, no? They leave behind holes which are also free to move around in the valence band and conduct electricity. No? So, doesn't necessarily mean na conduction band yung tawag sa kanya lang nagko-conduct ng electricity because holes exist, no? Holes can move around in the valence band. So, yun lang yan. Anyway, this gap in between is called the band gap, no? The band gap is the difference between the edge of the conduction band and the edge of the valence band, no? So, yun lang naman yun. And we classify the materials in terms, we can classify materials essentially in terms of the size of their band gap, no? So, for example, insulators have very large band gaps, no? Insulators have band gaps on the order of 8 or 5 electron volts of band gap. Semiconductors have nearly 1, no? Like silicon, for example, has 1.12 electron volts in the band gap, and metals have no band gap at all. Nag-overlap na yung valence band at conduction band nila, no? Which is why electrons are free to move around for metals, no? And you might ask, paano nila nalaman to? They solve the density of states for insulators. They solve the density of states for metals, no? So ganun nila nalaman to. By the way, we measure energy in terms of electron volts, no? So this is about the energy that it takes, or rather, no, di ba, potential energy against an electric field, no? So ang potential energy ng isang electron, for example, is kung 1 volt to, tas 0 volts dun sa baba, then the electron will actually kung negative 1 volt pala to, no? Oo, tapos 0 volt yung nasa baba, then the energy expended by the electron going from here to here is 1 electron volt, no? So charge kasi 1 electron yung charge niya, no? So that's 1 electron volt. And that's how we measure the energy. Now, this is interesting kasi if we measure things in electron volts for the energy band diagram, no? We can find na heat zaps electrons upward on average about 26 milli-electron volts upward, no? So gumagana sila, no? Kasi that's on average. Sometimes, no? Sometimes which results in about 10 to the 10, no? That's at room temperature. It's the heat is enough to jump the electron all the way, no? Kasi itong 26 milli-electron volts is what you'll find later pala, no? Later pa siya. Anyway, here. So, we have also this thing called the Fermi level or the Fermi function, no? I'll last slide na to, no? So I'll end it after this slide. But the Fermi function, no, tells us how likely we are to find an electron occupying one state or the other, no? So for example, ito yung Fermi function, no? Ito yung pataas dito, no? So, this function tells us at each point how likely a state in this level is how likely a state is occupied, no? So for example, at around here, no, if there were states here, no, there is half of those states will be filled and half of those states won't be filled, no? So that's all the Fermi function tells us, no? So this is the equation for the Fermi function, and it's dependent on the temperature, no? So we use the Boltzmann constant in EV and the temperature in in Kelvin, no? And the thing is, if we multiply K with 300, you get 0.026 electron volts, no? So that's where the 26 milli electron volts comes from, no? So lastly, temperature dependence ni Fermi level, ni Fermi function, no? Kapag kapag binaba mo yung temperature, no, to absolute zero, this becomes a flat function of 1 and 0, no? And what does that indicate? There is a 100% chance that the states down here are occupied. And there is a 0% chance that the states up there are occupied, no? So that means at 0 Kelvin, the Fermi function states that there are no electrons up in the conduction band and all of them are in the valence band, no? So yun lang naman yung sinasabi ng Fermi level. Okay? Sige. So with that, I'll stop the lesson here for today and we'll continue from here tomorrow, no? So I hope you guys have accomplished the attendance kung hindi nyo pa siya na-accomplish, and ingat kayo sa pagpunta sa susunod yung class. Thank you very much, guys. Online pa din tayo sa Friday, no? As we as mentioned. All right. Bye, guys. Feel free to ask questions on Discord, no? That's why we have that Discord.
Thank you po, sir.
Thank you po.
Bye,
Thank you po, sir.